How's it going? Good. Yeah, so today's going to really wrap up what's important from chapter 2, I think, which is, of course, we've gone through most of it. There's a few more sections that I don't really want to cover. What are we on, 2E right now? What comes after E? I'm really bad at the alphabet, A, B, C, D, E, F, F. That's on X circles. I think we should cover that, but it is sort of an optional topic. After that, I think is Morley's theorem. I'm not too worried about that. And then some optimization stuff about triangles. I don't think we'll cover that either. And then the only other really big thing that we absolutely have to cover in this class, I think, is Jevons and then Menelaus' theorem, which is chapter 4. So we'll probably jump straight from there, or straight from here to there. After that, though, we have a whole bunch of sort of optional topics. We could cover some stuff from chapter 3. There's some cool stuff in there, like cross ratios. And I mentioned beginning of the semester doing some compass and straight edge constructions and proving, for example, that some numbers aren't constructible, for example. So that's probably where we'll go. I don't know, but I'm feeling good about our pace. I'm feeling good about the fact that we're getting through everything we, I think, sort of absolutely have to in a higher level geometry class. A couple other announcements. I won't hold office hours today, so if you want to meet with me, just let me know and we can schedule something else. Grades for the exam 1 were posted up yesterday evening, I think. If you have any questions about those, let me know. I did some of that grading myself, and I put off writing the exam solutions to get that done because midterm grades are due Friday. So that's the first thing on my agenda. I'm gonna get the exam solutions done sometime today. I'll have those up online if you want to see mine. Although I will say grading your solutions has influenced the solutions I'm gonna write because some of yours are a little bit cleaner than what I was planning on doing actually. So anyway, let's see. Finishing 2E on in circles. We have really just one more big theorem to do today. It's Euler's theorem, which if you say Euler's theorem, you have to specify because there's a million different Euler's theorems. I believe this one, if you just say Euler's theorem in geometry, though, people would know which one you're talking about. So let's see, it's theorem. Yeah, so usually known as Euler's theorem. Although it really shouldn't have been named after him. It's, when did he discover this? I wrote it down. Well, he proved it in 1765. And apparently it was actually proven earlier. It was discovered later on. It was proven earlier, about 20 years earlier, by some other guy whose name I can't remember. But it tells us, what did we do last class? So at the end of last class, we proved that if, what was the very last result we proved? We proved that if the in-center and the circumcenter are the same point, then the triangle must be equilateral, right? So what if they're not the same point? The question is, how far apart are they, right? We can't prove anything like the in-center lies on the Euler line. It doesn't. But you still can ask, how far apart are these 2 points, right? So Euler's theorem gives us a formula for that. So here's Euler's theorem. In a triangle ABC, let little d be the length of the line segment IO, where I is, as usual, the in-center, O is, as usual, the circumcenter, and little d being the length of that, therefore represents the distance between those 2 points, right? Then, d squared, you sometimes see this written in different ways. Here's the form the textbook gives, which is a nice form. D squared is big R times big R minus 2R. Where both of these have the usual meaning as well. Big R is the circumradius, little r is the in radius. So for big R, it's the circumradius. And little r is the end radius, as usual. Turns out the proof isn't super easy. We're going to sort of go with a clever trick in proving this, but before we do it, we're going to prove a lemma that we'll use as well. And so here's our lemma. If a bisector of an angle in a triangle is extended to meet the circle at a point called P. At a point P, then P is equidistant from I. This doesn't mean anything so far, right? You can't be equidistant from a single point. It's got to be the same distance from I and something else. And it's actually equidistant from I and two other points. Equidistant from I and the two other points of the triangle, the two other vertices. And the two other vertices of the triangle. I feel a little bit off about the way I phrased that. Let me check something real quick. Distance repeated. All right, so what is this saying? Here's my circumcircle. Here I've got my triangle that's inscribed. I don't really want to draw it so my angle bisector looks like a median at the same time, so let's go. Let's get a little bit more funky with this. There we go. Okay. A, B, C. Draw on the angle bisector. So, angle bisector for this guy, probably a bit like that. And it's going to meet the circumcircle at this point P. So we've just extended this. All right, so where's I? Well, I live somewhere on this angle bisector, right? Remember, I is the point of concurrence of the three angle bisectors. If I drew in the other ones, I is probably somewhere around there, the center of the incircle. And what I'm claiming, what this lemma is claiming, is that this point P, by the way, this is one of the cool things about geometry. Now that we have all these interesting constructions and whatnot, you can pretty much always just draw some line somewhere and prove some facts about it. So the result here is that if you extend this angle bisector to P, P is the same distance from C, I, and B. And so IB is the same as BP, is the same as CP. That's what this lemma is saying. Any questions? Okay, So how are we going to prove this? Well, we'll only prove we'll prove one of these equalities. How about we prove PI is the same as PC? So we're going to show that those two distances are the same. How are we going to do that? Well, I want to show this is the same length as that. So what we're actually going to do is show that PIC must be an isosceles triangle. And the way we're going to show that it's isosceles is by proving that those two angles there are the same. Right, remember the isosceles triangle theorem goes both ways. If you're isosceles, then your base angles are the same. But if you have a triangle where the base angles are the same, then you must also be isosceles. So that's going to be our method of proof. That's what we're going to go with. I'll write that down again once we have some more space on the board. Okay, so proof. First thing I'll note is we will prove that IP equals IC. And the equality IP equals IB, maybe I should say the proof of the equality is similar. And let me just draw up a picture of what's going on again. All right, so angle bisector. And yeah, so let's, I'll just dot out this side. So there's one of those bisectors of C, and I'll draw this in. So there's the triangle we're looking at, right? ICP. We will show triangle ICP is isosceles, establishing, maybe I should say isosceles with base, IC, establishing that IP equals IC. How are we going to do this? Well, right, we want to work with these angles here. We want to show this angle is the same as this angle. And the reason we're doing that is because it's a whole lot easier to work with angles than lengths. And the reason angles are easier to work with is because we have all these different angles, all these different inscribed angles that subtend the same arc. So I can say some things here. For example, this angle and this angle are the same. Why? Well, because they both subtend the arc BP. Alright, so first, angle BAP, is it BAP? Yes, angle BAP is equal to, well, let's just say it's equal. We don't have to invoke the arc in this equality. It's equal to angle BCP, because they both subtend the same arc, BP. Well, how does BCP definitely what I want to look at. Sorry, I'm looking at the wrong angle here. BAP. How does that relate to the original angle A in the triangle? This is an angle bisector, so that's 1/2, right? So also, angle BAP, that's 1/2 of, and I'm just going to call this angle A. I know it's ambiguous in this picture, but it's pretty clear that we're starting off with angle A in our triangle, right? So when I refer to angle A, I mean just in the original triangle. So also, BAP is 1/2 of angle A, because AP is the bisector of angle A. And combining that with the result above, right, just substituting in, that means angle BCP is 1/2 of angle A. And so this angle here is also 1/2 of angle A. And combining this, or substituting in, or however you want to phrase this, combining this with the previous angle equality gives that angle BCP is 1/2 angle A. All right, so both of those angles are the same. This one is half of angle A, so this angle is 1/2 of angle A. Well, what's the angle we really want to look for? We're looking for angle ICP, right? Well, by additivity, I can say ICP, angle ICP, is this angle plus that angle. And what's this angle right here? Well, it's 1/2 of angle C, because IC is the angle bisector of angle C, right? So, hence, by additivity of angles, we have the following. Angle ICP, that is angle ICB, that's angle ICB plus angle BCP. By definition of IC, that's angle bisector C, so this first guy is 1/2 of angle C. I should really make my angle sharper. Again, a little bit ambiguous notation there, but when I talk about just a single angle, I mean the angle in the original triangle. So angle C plus BCP, we just showed that's 1/2 of angle A. Awesome. Now our goal is to show that the other angle here, CIP, is the same. So I will leave this here because we're going to want that again. How are we going to do this? I believe we want to claim that this angle is 180 degrees minus both of these. So yeah, so let's do that. Secondly, angle CIP. That's 180 degrees minus angle ICP. Plus this angle here that we can just call angle P, I guess. Or rather, let's phrase this slightly differently. Angle P plus angle CIP is 180 minus angle ICP. Am I phrasing this the way I want to go? No, I've brought this over the wrong way. Sorry, guys. I want ICP here. So we'll bring this term over and leave angle P over here. Sorry about that. No. What am I doing? Oh, I'm totally lost here. Let's start over. CIP, that's the one we want. CIP plus angle P. That's 180 degrees minus I'm using totally different notation than I used in my notes. IPC. Still I'm messing this up. The order here matters. Okay. Let's get this right. ICP plus angle PIC. This is my confusion. In my notes, I was thinking PIC was angle P. It's not. This is 180 degrees minus angle P. Minus, there we go. Okay. All the same form, right? All the exact same observations, and these three angles add up to 180, but on the fly, I was unable to adjust my notes and figure out which order I wanted this. So, I think we have this straight now. This angle plus this angle, so those two angles, equals 180 minus that angle. Okay, sorry about that. Now we want to make a substitution. What else does angle P equal? It subtends the same arc as something else in this picture.
ABC.
Yeah, it subtends the same arc as angle B. So that is 180 degrees minus angle B. And here, this is because angle P and angle B subtend the same arc. And what's 180 degrees minus angle B? Well, that's the sum of the other two angles in the triangle, right? That would be angle A plus angle C. Now we have arrived. Can I show from here that this is the same as this? Well, usually I wouldn't be able to, right? Usually this equality, just this alone, doesn't mean that this has to be the same as this. But angle ICP, we already have a form for that, right? In fact, without even having to sub this in or anything and then do the algebra, ICP is 1/2 of this expression, right? So PIC must be 1/2 of that expression as well, because when you add them together, you get that expression. So how about we call this equation star, we can refer to it quickly. Subbing in star for angle ICP gives the desired result. Angle PIC is also 1/2 angle C plus 1/2 angle A, which is the same as angle ICP. So after getting completely lost there in the middle of trying to figure out exactly what we want to do with these angles, we're there now. We've established that these two base angles are the same. Therefore, this is an isosceles triangle. Therefore, those sides are congruent. Right? So, showing that triangle ICP is isosceles with PI equal to PC. Any questions? And the big problem was in my notes I didn't call this angle P, I called that angle IPC. And with all these things mixed together, ICP, PIC, IPC, it's confusing. So I think this is better notation, just calling these things angle A, C, B, and so on. So it's a lemma because it's a technical result, right? It's not the most mind-blowing result in the world. It's just a technical result that when you extend these angle bisectors, the distance of that meeting point with the circumcircle is the same when measured from either vertex or to the in-center. And it's a lemma because one, it's technical, and two, we'll use it to prove the big result. Proof of Euler's theorem. If you look up proofs of this, you will find many of them. Sometimes lots of proofs of various theorems aren't particularly readable because they invoke other bits of knowledge that we haven't gone through yet, so it always sort of depends on the order in which you build things. I like the book's proof. It's really clever. It uses this idea. So if I defined precisely every single point, we'd be writing quite a bit. So I'm just going to draw a picture, label some points, and say let all these points be as drawn. So let's see. How many points do I need here? A, B, C, here's my triangle. We'll extend this angle bisector as we just did. So we'll extend that to point P. And I think all we need for now, we'll draw some more stuff on here. I looks, maybe it's a little bit higher, but anyway. I is maybe right around there. Probably should be a little bit higher up on that line. And the circumcenter, I'm just gonna put it at, I know it's, where's the circumcenter? Could be somewhere around there. There's the circumcenter O. So let's connect these 2 points. Let's connect these 2 points. And what we're trying to find is the length of that line segment, IO, right? That's D. So here's the first thing we're going to do. We're going to extend this line segment. If you don't mind, if I extend it in this picture, it'll be okay. Let's draw it a bit more parallel. Oh, okay. I want to extend this line segment so that it meets the circumcircle. And in this case, it'll be an actual diameter, right? It doesn't look like it in this picture because I've moved the circumcenter up a little bit, but this is the center of the circle. This is a chord passing through the center, so it's a diameter. And we'll extend IO to meet the circumcircle at 2 points X and Y. And so extend IO as shown to meet the circumcircle at points X and Y. This is what I mean by I'm not precisely writing down the definitions of these points, right? If I just wrote this without a picture attached to indicate exactly what was what, that's ambiguous, right? Is this X or is that X? Right? I'd have to write some more and say X would be on the opposite side of I as O is, and Y is on the opposite side of O as from I, right? I'd have to be precise there. But to save some writing, we'll just go with the picture. And we'll let little d be the length of IO, as in the statement. Then I want to measure 2 lengths in this picture. What is the length of xi? Well, just in terms of d, I could think of this as, what's the length of xo? That's big R, right? That's the circumradius. So this would be the length from x to O minus the length from I to O. So that would be capital R minus D, right? So this is big R minus D. And what about I to Y? What's IY? Or yeah, we'll call it IY. What does IY equal? Well, that would be big R plus D. And so that's big R plus D. And what if I multiply them together? Then xi times IY. That's R minus D times R plus D, which is big R squared minus D squared. And that's a difference of 2 squares. So that's cool. I'm already getting expressions that are starting to look or feel a bit like Euler's theorem. I've got this D squared in there. I've got R squared. The problem is that equals the product of these 2 line segments that I'm not going to be able to figure out what these are individually equal to in terms of in radii and circumradii and whatnot. But here we can invoke a theorem that we haven't talked about since we first proved it, which is xy is a chord through I. Right, do you remember doing anything with products of segments of pieces passing through a point? We haven't talked about products too often in this class, so this came up once. I believe it's theorem 1.35 in the book that says that if you take a chord through any point and measure these two distances, or the product of these two distances, that product doesn't depend on the chord that you choose at all, right? Remember, it was independent of the chord. It depends only on the point. So if I take another chord through I, which in this case is AP, the product AI times IP should be the same as XI times IY. And it turns out that AI and IP are two different segments we can say stuff about because AP is the angle bisector. We'll be able to work with that. So now, by theorem 1.35, we have that AI times IP. Is that how I phrased it now? AI times IP is equal to XI times IY. And that's also R squared minus D squared. So these two segments, we're not going to be able to work with them. But these two segments we can work with. We can replace those with expressions involving little r and big R. So how are we going to do that? First things first. What's PI equal to? As we just proved, it's also the same as PC. All right, so let's draw that length in there. Then I have a triangle. I have a triangle that I can work with, triangle APC. And so we're going to apply the law of sines to that angle. So applying the law of sines to triangle APC, we have that length PC over sine of this angle. What's this angle? Well, this is an angle bisector, right? So it's 1/2 of angle A. So that's A over 2. In fact, this is not just the law of sines. We're invoking the extended law of sines. That equals twice the circumradius. So that's 2 times big R. All right, so that means that PC is sine of A over 2 it's an ugly form, but I'll leave the 2 at the end there, 2. Is that okay? Just applying extended law of sines to this triangle? So now, like I said, we wanted to figure out stuff about these lengths, but IP is the same as PC. So, by our lemma, IP is the same as PC, so IP is sine of 1/2 of A times 2R. And I think now I can plug this into this equation, and finally I can erase it. So substituting into, once again, into equation star, substituting into star, we have that, let's rearrange the order here. 2r times ai times sine of a over 2. Alright, just plugging in for IP into this equation. So 2r times ai times sine of a over 2 is big R squared minus b squared. Last but not least, we need to get rid of that stuff. We need to write that stuff in terms of big R and little r. How are we going to do that? Well, here's the last trick. That looks like we're doing triangle trig, right? That looks like if I look at sine in a right angle triangle, SOHCAHTOA, I can express sine as opposite over hypotenuse. So let's try to construct a right triangle here. And all I'm going to do is go to I and drop a perpendicular. So we'll call that point F, so that's a right triangle now. So finally, let F be the point on AC so that IF is perpendicular to AC. This gives a right triangle. This gives a right triangle, AIF if you want. Triangle AIF. So in triangle AIF, again just doing triangle trigonometry on this, sine of this angle, sine of A over 2, is opposite IF over hypotenuse. I could call this IA or AI. I've been calling it AI in the past, so to make my proof not as confusing, I'll call it AI again. What's the length of IF? Well, remember how we get the points of tangency of the incircle, right? You come into I, you drop a perpendicular, and your incircle is tangent at those points, right? So the length of IF, that's little r. That's little r over AI. And that means that AI times sine of A over 2 is little r. So we'll call this equation double star now. And substituting that into double star gives us Euler's theorem. Substituting this into double star gives us 2r times little r is big R squared minus d squared, which is Euler's theorem. Written in a slightly different form, but not hard to solve with d squared. So we're done. So this is a clever result, right? If I assign something like this for homework, I would expect you to struggle with this. I'm not even sure I would expect most people to be able to prove this, because it requires this clever idea of, let's extend this line. And then once we've extended it, so we have this chord across the circumcircle, let's note that we have this other chord, and we can work with those pieces as well. So it is a clever proof. It's not just writing down the definitions and then some congruent triangles fall out of it or something. It's a tough one. We have about 2 minutes, so I will just state this corollary. Which is sometimes known as Euler's inequality. Really quick corollary. This is Euler's inequality. Which says that big R is bigger than or equal to 2 times little r. So the circumradius is at least twice as big as the end radius. And we had made this observation last time. I think I'd convinced you of this by invoking stuff about the 9-point circle and the radius of the 9-point circle. I think I said strictly bigger there because I had forgotten about the case where they could be equal, which is equilateral triangles. So there's the inequality with equality if and only if the triangle is equilateral. We have 1 minute, so I will prove the first part. A quick proof of first part. What do we have? We have big R times big R minus 2R. That's equal to d squared. Well, what's the smallest d squared can ever be? 0, right? Squares can't be negative, so that's bigger than or equal to 0. What about big R? Is that ever negative? Can't be negative, right, by construction. In fact, it can't be 0 either. Obviously, for any triangle, it would only be 0 if you have a single point. So big R is bigger than 0. So what's the only two ways, or what's the only way a positive times another number can be positive? Is if this guy is bigger than or equal to 0. Right, so that implies that R minus 2R is bigger than or equal to 0, which is Euler's inequality. Big R is bigger than or equal to 2R. The second part's not hard. It's in the textbook though, you can read it if you want. But we already proved last time exactly what you need, which is if I and O are the same point, then you're equilateral. And if they're the same point, then E would be 0. So we'll stop here. And I guess we'll move on to what did I say comes after E? Yeah, we're doing E right now, so 2F. We'll talk about X circles. I think they're important. I looked at what Mark Honasek did in the past with his class. I think he skipped it, but I think they're important enough to mention. And then we'll jump straight into chapter 4, I think. So, see you guys on Friday.